Hi everyone, welcome to our Slide 3 webinar series part 3, which is about probabilistic analysis for 3D slope stability. My name is Sina Javan-Khoshtel. I am a geomechanics specialist at Rocscience. Today I have with me Miss Brigitte Kami, who is the geotechnical software developer at Rocscience. She has a master's degree in statistics, and she's responsible for developing statistics options in our software packages. So today we're going to present this together. We are Rocscience, located in Toronto, Canada. We are the world leader in developing 2D and 3D software packages for civil and mining and geotechnical applications. For over 20 years, we have more than 8,000 customers, and at our office in Toronto, we have 50 employees, which half of them, they hold advanced degrees in engineering. We have had 2 webinars so far. Part 1, I talked about 3D slope stability analysis. Part 2, seepage and support analysis, and today, we are going to talk about probabilistic analysis for 3D slope stability. This is a new option that we developed in Slide 3 M+ version, which was released a couple of months ago. And we're going to talk about different features that we have in this software. Please feel free to write down your questions at the questions section of the GoToWebinar software. And we have some time at the end, and we're gonna respond to your questions. In this presentation, I'm gonna start with the basics of probabilistic analysis. The first question that everybody asks is, why should we do probabilistic analysis at all? So we're gonna answer this question, and after that, we're gonna talk about the features in the software. Probably I've seen a lot of these charts, which are deterministic charts to calculate factor of safety. The input parameters for these charts are soil properties and slope geometry, and the output is going to be the factor of safety. However, this factor of safety is not enough for design purposes because it cannot account for uncertainties that we have in our design. So what are these uncertainties? The most important one is inherent spatial variability of soil properties. Others are scarcity of data, changing environmental condition, unexpected failure mechanism, model uncertainty, and human error. So with all these uncertainties, we cannot design a slope with just one parameter, which is a factor of safety. There are different reasons that engineers, they don't like or they don't use probabilistic analysis. The first one is because of, as geotechnical engineers, our statistical knowledge is very limited to a few courses in bachelor's degree. And we don't have that much of probability theory knowledge. Also, engineers are more comfortable with deterministic analysis and just use factor of safety. There are some misunderstanding about the probabilistic analysis that it requires a lot of data, time, and effort, which is we're going to show you today that it's not the case. And also, the availability of the software in the market, especially now that we are presenting the 3D probabilistic analysis, there are not that many commercial software to do 3D probabilistic analysis, if there is any, other than Slide 3. And at the end, some people think that probabilistic analysis is a replacement for deterministic factor of safety, but it's not the case. A probability of failure and factor of safety, they have to be used together for design purposes. To measure these uncertainties that I mentioned, we use a parameter called coefficient of variation, which shows the level of uncertainties in input parameters. It's defined as the ratio of the standard deviation by the mean value of the soil properties. There are a lot of studies, such as this table that you can see here, and we have some of these tables in Slide 2 and Slide 3 software. which we provide the recommended values for the coefficient of variation of input parameters. For example, in this table, you can see that for underend shear strength at the top, the range for the cohesion is from 10 to 55%. So let's assume you have a 55% of variation in your cohesion. In this case, you cannot just rely on the deterministic analysis, and you have to consider the probabilistic analysis. There is another reason for this deterministic versus probabilistic analysis, and the reason that we should use probabilistic analysis. Let's look at this example. This curve, a slope A, has the mean factor of safety of 1.7 compared to this case, which has the mean factor of safety of 1.5. So as an engineer, you expect that a slope A is safer than a slope B. But if you look at this area, which is the area under the distribution curve of the factor of safety for the values of factor of safety of less than 1, which is the definition of probability of failure, you can see that for a slope A, this light gray area is larger than a slope B, which is a dark gray area. In other words, probability of failure in a slope A is higher than a slope B. The reason for that is this number. Coefficient of variation of a slope A is double the coefficient of variation of a slope B. So even though a slope A has larger mean factor of safety, it is not safer than a slope B, and it has a higher probability of failure. That's one of the reasons that we need to do these together. Both factor of safety and probability of failure, we have to use them in our design purposes. So these two figures, they show deterministic analysis versus probabilistic analysis. The left figure is the deterministic analysis that people assume only one number for the entire profile. Let's say we have a cohesion of 2, so we just use 2 for the whole geometry. In the probabilistic analysis, instead of using one number, we use a distribution for the parameter. And then when we have a couple of simulations, for each simulation, we pick one value from the distribution curve of the input parameter. And at the end, and we calculate factor of safety for each simulation. And at the end, we count the number of simulations with factor of safety of less than 1 divided by the total number of simulations. And that's going to be our probability of failure. So instead of considering only one case, we consider thousands of cases to make sure that we covered everything. So next step is how we can set up a probabilistic analysis in any of our software. It doesn't matter, Slide 2 or Slide 3. The first step is to define the distribution for each parameter. To define a distribution, you have to define the type of distribution, mean, standard deviation, and relative mean and relative max. The lower bound of a distribution is defined by mean minus relative mean, and the upper bound is going to be mean plus relative max. Bridge is going to show you how it looks like in an example. We have different types of distributions. The most common ones, and especially if you don't know what distributions your data follow, are normal and log normal distributions. Normal is the most widely used because mostly it's symmetrical. But we recommend for the geotechnical applications to use log normal because it is positively skewed. It means that it doesn't give any negative number. And it's best for geotechnical applications and especially soil properties because they are always positive. If you have data, you can find your type of distribution, but as an input parameter, you can have any of these distributions in the slide software: exponential, beta, gamma, triangular, and uniform distributions. About relative mean and relative max, sometimes you don't know what ranges you use. That's why we have an option in the slide software, which is called 3x or 3 sigma rule. Three sigma rule in statistics means that 99.74% of all values of a normally distributed variable fall within plus or minus 3 standard deviation of the mean. So if we have 3 standard deviation above the mean and below the mean, and this is our distribution, we are making sure that 99.74% of our data is within this distribution. There is another use for three sigma rule. If you have data and you know the highest conceivable and lowest conceivable data, then you can use this equation HCV minus LCV divided by 6 to find your estimated standard deviation, which is another use for the three sigma rule. Now we need to generate n samples for each property. I'm gonna pass the presentation to our developer and statistician at Rocscience, Bridget, and she's gonna walk you through this process. I'm gonna come back with a few more examples.
Thank you, Sina. Hi, everyone. Just a reminder, if you have any questions, please type them into the question box. So now that we've decided, for example, that cohesion follows a normal distribution with a mean of 2, we need to sample that distribution. And to do that, we need to set up these three options. The first one is the sampling method. The second is the number of samples, and the third is which slip surfaces we want to analyze. So we'll go through these three now. The sampling method, there are three options: Monte Carlo, Latin hypercube, and response surface. Monte Carlo is a brute force method. Basically, it just randomly samples the distribution you've defined. With Latin hypercube, the distribution is divided into sections, and each section is sampled, which ensures that the entire distribution has been covered. With response surface, you sample a smaller number of samples than requested. You train a model which can predict factor of safety, and then you plug in your 1,000 samples and it predicts 1,000 factors of safety. So which one of these should you use for your analysis? The Monte Carlo, like we said, is a brute search method. It's the traditional method. The only reason to use this is if you're comparing to a paper or something like that. Otherwise, there's no need to use it. Latin hypercube is much more accurate than Monte Carlo. You need about 1/5 of the samples you would need with Monte Carlo to get the same result. So certainly between Monte Carlo and Latin hypercube, you should always choose Latin hypercube. Response surface, on the other hand, is specifically if you're doing an overall slope analysis. In 3D slope stability, such an analysis is quite time consuming. So you use response surface, which creates that training function to save time. And we'll show an example with that. The second option, the second parameter you have to set is the number of samples. So this basically means here's our distribution with mean of 2. How many times do we want to sample it and calculate factor of safety? There are various ways of determining how many samples you need. There are a lot of papers that have functions, which are functions of the number of random variables you have, or other such things. But really the best way is to do a sensitivity analysis and to see how many samples do you need for the probability of failure to converge. And the final setting you have to set is the analysis type. Here we have global minimum, overall slope, and multiple minima. With global minimum, basically a deterministic analysis is computed first. You find the global minimum surface, and then those samples that you got, you plug those in and get the factor of safety for that same surface. So for example, you sample cohesion 1.5, plug that in with that same surface, get the factor of safety, and so on. With overall slope, you don't assume a surface. So you plug in your samples and a different surface might be found in each simulation. Meanwhile, with multiple minima, so when you first do a deterministic analysis, you search a bunch of different surfaces and you find the global minimum. So with multiple minima, instead of just using the global minimum and changing the cohesion around it, you use all of those surfaces that were searched and you plug in different samples. So basically it's better than global minimum. So again, which one of these should you use? Global minimum, you should only use it for very simple geometries or for back analysis. Overall slope is the most accurate because it finds a different surface each time. It's also the slowest because it's the most rigorous. But really, for any probabilistic analysis you do, you should do an overall slope analysis, Latin hypercube overall slope analysis, just to make sure you haven't missed any weak regions. And the multiple minima is sort of the middle ground between global minimum and overall slope, both in results, it's more accurate than global minimum, and in computation time. Okay, so now we have sampled our cohesion distribution. We take each one of those samples. So for example, we take this sample of 0.7, we plug it in, we get factor of safety for that simulation, and so on for each of our 1,000 simulations. And then we can calculate the probability of failure, which is the number of simulations with a factor of safety less than 1 divided by the total number of simulations. This is also the same as the area to the left of the factor of safety equals 1 line in the factor of safety distribution. Okay, so now we'll do some live examples. We have 5 examples in this presentation. The first one we'll do is just a simple extruded slope. Here we'll just go over how to set up the probabilistic analysis. We'll just do one random variable, and we'll explore what's the difference between all those options we talked about, global minimum, overall slope, etc. And then we'll also do a back analysis. Okay, so I've opened slide 3 here. I'm in the geometry tab, and I'm going to create just a simple slope with the slope wizard. I'm going to keep all the default settings. And yeah, that's the slope. Now I'm going to open the material properties dialog. So the default material is more Coulomb. I'm going to keep everything, default parameters and everything. And then I'm going to go to the slip surfaces tab and open the search settings. Now here I'm going to do something which we should not do and dumb down the search, just to be quick for this case. And it's a pretty simple case, so it should be all right. Okay, so now to turn on statistics, we're going to go to project settings and click on the statistics tab and turn on probabilistic. So here are the options we talked about. The defaults are set. Global minimum 1000. We're going to switch the sampling method to Monte Carlo for now. Okay, so now we see this statistics menu has shown up. So we're going to click on statistics, material statistics. And for material 1, the only one we have defined, we're going to add a random variable. So these are the options for more Coulomb. I'm only going to do friction angle right now. And these are our distribution options. And I'm only going to do normal right now. Okay, so the mean is 35. I'm going to set the standard deviation to 7. And then I'm going to click this 3 times button, which does the 3 sigma rule that Sina talked about. So basically what that did is it multiplied the standard deviation by 3 and it plugged it in here and here. And what that means is that the distribution we have defined has a mean of 35, and the lowest possible value is 35 minus 21, or 14, and the highest possible is 35 plus 21. So then we're going to click OK, and we're going to compute. So global minimum is actually very fast. So first it's going to find that deterministic slip surface, and then 1,000 times it's going to plug in different values. So now we're going to go to computed results. There are 2 things we see here. First is the deterministic factor of safety, about 1.17, and the second is the probability of failure, which is 26.6%. So 26.6% of our 1,000 simulations had a factor of safety that was less than 1. So that means basically that 266 of the 1,000 failed. There are several plots we can create now. So I'm going to go to Statistics, Scatterplot, and I'm going to set the horizontal axis to friction angle and vertical axis to factor of safety. And click Plot. And here we can see friction angle on the bottom, factor of safety on the y-axis. As expected, as friction angle increases, factor of safety increases. We can also see that friction angle ranges from about 15 to 50 something, which is the range we defined in the material statistics. And another plot we can make is the histogram plot. So I'm going to create a histogram plot of the factor of safety, and I'm also going to highlight factor of safety less than 1. Okay, so these are all the factor of safeties that were computed. So you can see they range from about 0.5 to 2 point something. And this green area represents the probability of failure, so the area under the curve. And like we said, the probability of failure was 26.6%, which you can see here. And that means 266 points had a factor of safety less than 1. Now I'm going to change the data of this plot, and I'm instead going to plot the factor of safety, the friction angle random variable. So this is what the friction angle looks like. So it's again between 15 and 51, and I'm going to turn on the input distribution. So this green line is the theoretical distribution we defined with a mean of 35 and so on. And the yellow bars are what we actually sampled. Okay, so that's Monte Carlo. Now I'm going to go back to project settings, and I'm going to switch to Latin hypercube and click OK, still doing global minimum, and compute. So again, the deterministic surface is found first, and then just the friction angle values are changed around it. Okay, now I'm going to make that same histogram of friction angle. And then I'm going to tile my windows. Okay, so now we can see on the right was the Monte Carlo case, on the left is the Latin hypercube. So because Latin hypercube divides the distribution and samples each section, it's more accurate. It more accurately reflects the theoretical distribution we defined. Okay, so for deterministic analysis, you can always view all the surfaces that were searched to find this global minimum surface. So I'm going to click the Show All Surfaces button. And these are all the deterministic surfaces that were searched to determine that this is the global minimum. So like we said, when we have global minimum selected, global minimum probabilistic, then only this surface is used and the friction angle is changed in each simulation. But if we select, for example, multiple minima, then all of these surfaces which were originally searched are used, and the friction angle is changed around them. So that makes it a little bit more accurate than global minimum. Now, the other use of global minimum is doing a back analysis. So I'm just going to do a simple back analysis. Say we know already what the failure surface was, and we want to find out what friction angle led to that failure. So what I'm going to do is import a DXF file with the failure. So just construction. Okay, so I'll delete the results we had previously. Okay, so this is the surface that we know failed, for example. So now I'll go to Surfaces, Add User-Defined Slip Surfaces, General, and I'll set this surface as the failure surface. And I'll also change our surface search. So I'll go to Surfaces, Slip Surface Options, and I will change our search from search method to user-defined surfaces, and click OK, which means only the surface will be searched. Now, if you're doing a back analysis, probably you don't know that the potential friction angle values follow a distribution. So more likely you would just say it's in a range. So to do that, I'm going to say friction angle is uniform and it ranges between these values and click OK. Okay, so now we can compute this. And we can go to Statistics, Scatterplot, and make that same plot from before. And now I'm going to highlight data that is in a range. So basically, I want to know at what friction angle is the factor of safety 1. So I'm going to set the range to 0.98 to 1.02, for example, or whatever you think is best. So then we can see the highlighted range here, and we can zoom in. Oh, too far. Okay. And see that the friction angles that led to a factor of safety of about 1 range from 28.3 to about 29.2 degrees. Okay, so that's how you would do a back analysis. Now I'm going to change the search back to our search method. And I'm going to delete this failure surface. And I'm just going to show you what an overall slope would look like. So far we've only done global minimum. If we did overall slope, it would look like this. So instead of just finding that single deterministic surface, it's going to do that 1,000 times. So now it started looking at the second sample, for example, doing the second surface, and so on. So I'm going to stop that because it's not a live demo type of example. And the other thing I want to show you is what response surface is doing. So now if we stay in overall slope, but change the sampling method to response surface, remember that response surface takes a small number of computations and trains a model. So here we still define 1,000 samples, and we click compute. But here, instead of 1,000, it's only going to compute 15 in this case. So basically, it knows we have one random variable defined, and it's going to compute a number that it deems necessary to train the model. Okay, so now we have a general idea of how to set up the probabilistic analysis and what the options are. We'll do a more complicated example. So this is the open pit example. Here we have a proper search with optimization, cuckoo search, GLE method, and we have 4 random variables over 2 materials. There's a mix of normal and log normal distributions with fairly wide ranges, so big standard deviations. Okay, so this first model is probabilistic, and it's Latin hypercube with global minimum. So remember that means that the deterministic global minimum surface is used for all 1,000 of these simulations. And we can go to statistics, material statistics, and see the random variables. So the same ones from the table, cohesion and friction angle for sandstone, some more random variables for limestone. So the global minimum results look like this. This was the deterministic surface. The probability of failure was 4.8%. We've also computed an overall slope case. So I'm going to switch to that one. And just to show you, this is project settings, statistics, overall slope now. So again, remember that means in each simulation, a different surface might be found. So now if we look at the results, we see the probability of failure is 8.4%, whereas with global minimum, it was 4.8. So it's almost double, which shows the importance of overall slope. And the other cool thing we can do here is we can show all surfaces, which shows, in this case, when doing an overall slope, all of the surfaces that were found in the 1,000 simulations. So for example, here's one of the surfaces. If we click on it, we can see this was the cohesion value that was sampled for the first material, this was the friction angle, etc. And this was the factor of safety value for that simulation. And these are all of the surfaces that were found. So you can see deterministic only finds the one. If you do overall slope, you find potentially other failures. For example, even there's one over here. Okay, so that one was overall slope. We also did response surface. So response surface, sampling method response surface, again 1000 and overall slope. This time the results were 8.6%. So almost the same as the regular overall slope, 8.4% versus 8.6%. So, and again, we can view all the surfaces. So again, you might ask, so what's the difference if they give about the same result? Why would you use one or the other? Well, the Latin hypercube overall slope model takes about 25 hours to compute. With response surface, it takes about 1 hour. So that's the point of response surface. It's just the computation time savings when doing overall slope analysis. And like we said, this computes a smaller number of samples and trains the model. So if we look here at all of the surfaces that were generated, we can see that 70 samples were computed in this case, plus the deterministic. And if we look at all the surfaces, we can see that there's less of them, but it did sample all of the same regions. It found all the same failures. And you might be wondering, okay, so 70 simulations were computed here. Isn't this just the same as, wouldn't you get the same answer if you computed 70 Latin hypercube simulations? Which we also did. So if you go here to project settings, we did Latin hypercube with 70 samples and overall slope. But in this case, the result was 10%. So you can see that doing just 70 simulations is not the same as when response surface trains a model with 70 simulations. Okay, and here we've just summarized our results. So like we said, Latin hypercube overall slope was 8.4%, response surface overall slope 8.6%, but the difference is really just the time savings. 25 hours for Latin hypercube, 1 hour for response surface. And we also plotted the two factor safety distributions for Latin hypercube and response surface. And we can see that they're in very good agreement. They both capture this other failure mode over here. So you might be wondering what exactly is happening in response surface. And it's something like this. So basically different combinations of strategically selected samples of our random variables are computed. So in that case, there were 70 combinations and the factor of safety is found. And they're used to train a model like this. It's basically just a big polynomial. And once the model is trained, then we can plug in the 1000 samples we actually wanted and get a predicted factor of safety for those 1000 samples in a fraction of the time. But one thing that's important to note is that although we here have done tons of verification examples and the results have been really good, still response surface is predicting the factor of safety. So we always recommend running an overall slope Latin hypercube analysis overnight. And now I'll pass it back to Sina for the remainder of the examples. Thank you.
Okay, thank you, Brigitte. I think Brigitte talked enough about the basics of the methods that we are using in slide 3. I'm going to show you a couple of cool examples with civil and mining application to see what's actually the application of this probabilistic analysis. The first example is a landslide. I created the geometry in webinar 1 and webinar 2. Speaking of these webinars, you can go to Rocscience website and sign up and see the link which goes to the previous webinars that on YouTube channel of Rocscience, and you can watch them online. This one is going to be available in a few days as well. Okay, this example, we have 3 different materials. Each material has its own cohesion and friction angle as random variables. You can see all log normal distributed parameters. I use cuckoo search with a Spencer method for the limit equilibrium analysis, and the deterministic factor of safety is 1.48. Let's look at the model. This is the model. We have done the probabilistic analysis with probability of failure of 1.5%. If I turn on all the slip surfaces, you can see that we generated 1,000 slip surfaces. If we go to project setting, you can see that it's Latin hypercube with overall slope option and with 1,000 simulations. So for actual case studies, what you need to do is always use overall slope option with either Latin hypercube or response surface, and as Bridge recommended, both. So you can see that the probability of failure is 1.5, and these are the regions with the lowest factor of safety from different simulations of probabilistic analysis. Before I continue on the probabilistic model, I'm going to go back to the deterministic model, which we just calculated factor of safety. I'm going to prove again why we need to use probabilistic analysis together with deterministic analysis. If we look at all the slip surfaces that we generate for just deterministic factor of safety, you can see these are all the surfaces for one deterministic analysis. And when you do the deterministic analysis, these surfaces are generated based on the mean value of the input parameters. Like if you have cohesion with any mean value or friction angle, we use the mean to generate these surfaces and to calculate factor of safety. Now, if we compare actually these two cases, the deterministic one and the probabilistic one, you can see that the failure surfaces that are generated for deterministic analysis ignore some part of our geometry. In probabilistic analysis, the focus is on this region, but there are cases, there are combinations of soil properties that are generated randomly that create these slip surfaces that they are at some other locations in your geometry. That's why we recommend to use probabilistic analysis, because deterministic analysis sometimes cannot capture the critical cases, and only using average properties to generate one slip surface is not enough. So I'm going to go back to the probabilistic analysis. For this model, I created a 2D section as well. As I mentioned in the first and second webinar of slide 3, most of the people are more comfortable with the 2D analysis, and that's why we have an option that you can create a 2D section cut, and you can take it to the Slide 2 software. In the probabilistic analysis, when you do that, and when you compute this section, it's going to compute it probabilistically, not just deterministic analysis. But it only shows the deterministic factor of safety. So the deterministic factor of safety is 1.44 compared to 1.48, which is the deterministic analysis in the 3D. The reason for that is our cut is exactly in the middle of the 3D failure. So if your cut was here, you couldn't get the same number, close number to the 3D case. I'm gonna go to our slide model, the Slide 2 model, to see the differences between the cases. First of all, probability of failure is 1.8 compared to the 3D one, which is 1.5. So factor of safety, deterministic factor of safety in 2D is less than 3D. On the other hand, the probability of failure in 2D is larger than 3D. The other thing that you can see in this model is the same as 3D, different regions for the critical failure surface, probabilistic critical slip surfaces. And as you can see, we have the top of the model similar to the 3D one and other locations. This is called multimodal failure, and in all this limit equilibrium software packages, you only get this, the deterministic factor of safety together with its failure band. But in the future versions of Slide 2 and Slide 3, we're gonna have multimodal failure, because most of the time, similar to this case, and especially it's good for probabilistic analysis, one mode is not enough, and multimodal would be the answer. So you can see comparison between 2D and 3D, they match perfectly fine. So if I go back to the presentation, this is the comparison that we had, and these are the results. Let's move on to the next example. This is another open pit, but much more complicated, several layers of soil properties. And let's look at this model. The only thing for this model is these are the parameters, and you can see we have 4 different types of material properties with that they are log normally distributed, and the deterministic factor of safety is 1.6. This is the model. If you want to see how complicated it is, you can look at this view, different material, different sections. And for this one, because it was more complicated, we used 3000 Latin hypercube simulation, which is equal to about 15,000 Monte Carlo simulation. And again, we used the overall slope option. And for the methods, we used a Spencer. We always recommend to use either GLE or Spencer for your probabilistic analysis. If we look at the results, this is the critical slip surface with the factor of safety of 1.26. And if we look at all the slip surfaces from different probabilistic analysis, you can see that we have 3000 critical slip surfaces generated for this model. And again, if I move the model, you can see that this is not just this region. We have other regions of failure that the probabilistic analysis cut these regions. Okay, let's plot a few histograms. Let's look at the factor of safety histogram plot. This is the region with the factor of safety of less than 1, probabilistic region. 1018 critical cases out of 3000 failure surfaces, and the best fit for the distribution of the factor of safety is log normal. If we go back to this model, another histogram, you can look at cohesion, for example, for the first material. And if we turn on the input distribution, you can see that 3000 they were enough to generate the actually the input distribution that we defined for cohesion. The other thing that you can do, and it's very interesting, is to use the scatter plot to see how sensitive is your factor of safety to different parameters. For example, if we plot factor of safety, a scatter plot versus cohesion, this is the regression line, and you can see as the cohesion goes up, factor of safety goes up as well, which makes sense. But we don't know how much factor of safety is sensitive to cohesion or friction angle, for example. So if I plot factor of safety versus friction angle, you can see the how steep is this regression line compared to the case that we plotted against cohesion. So our factor of safety is more sensitive to friction angle compared to cohesion, which means that in a statistical word, if you have more variability in friction angle, it's gonna affect your probability of failure more compared to the cohesion. However, you have to keep it in mind that the variability of friction angle is at most 20%, but cohesion can go up to 50%. But up to 20%, if they have the same variability, the effect of friction angle is more on the probability of failure. As I showed you in this example, I used the Latin hypercube model. But I have another example which we use response surface method. And you can see for Latin hypercube, we had to use 3000 simulations. But for response surface, as Bridget also explained, we only need 329 samples. And you can see with this factor of safety, with response surface, we get probability of failure of 30%, but with Latin hypercube, 33%. So the difference is negligible. But if we go back to the presentation, I'll show you how the time is different. So with response surface, probability of failure of 30%, 2 hours it took to do the probabilistic analysis for this model. But with Latin hypercube simulation, probability of failure of 33%, it took 35 hours. So now you can see that why response surface method is important for complicated cases. Let's make it a little bit more interesting. As you know, probably we developed spatial statistics in Slide3 software in 2018 version. And if I want to explain it to you, let's say we have this model. To define the spatial statistics, in the statistic dialog, we have this spatial option. And if we go to material statistics, you can define the correlation lengths in horizontal and vertical direction. For this model, I just have one random variable, which is cohesion. And we have something called property viewer that you can look at your spatial field. So we have 1000 simulation, you can change it. These fields are going to change 1000 times, and we do probabilistic analysis. Currently, we don't have this option in Slide3, but I'm going to show you how you can model one sample in the Slide3 software. Normally, horizontal correlation length is very large compared to the vertical correlation length. So this is the actual behavior in the field. So we have horizontal layers, and correlation in vertical is smaller. Let's say the second one, this one is nicer, so I'm going to pick this one. So we have different weak regions and strong regions for this model. One option that we have in Slide2 is to export this sample, this model, as discrete function. When you export it as discrete function, which I'm gonna do for each material, you can do it separately. I already have it, but I'm gonna replace that one with this guy. And if we go back to our material properties, we have an option called discrete function. So you can import it to any Slide2 model, a Slide3 model, even RS2, which is a 2D finite element, to run one simulation and see if the factor of safety in 2D matches between limit equilibrium and finite element, or 2D and 3D they match. So if I define this discrete function, I can import this, and you can see what we have is, this is drained. We have X, Y, cohesion, and friction angle, which is constant. So we can take it to 3D and create a discrete function, 3D discrete function, which I did. And this is the same slope. I just extruded the slope, and I had the same discrete function at 5 different locations, which means that I assumed on this direction I don't have any variability. I only have variability on X and Z here. On Y direction, there is no spatial variability. To show you how it works, you can see soil 1 is defined with a discrete function. And in my discrete function, the Y changes because we have different locations, but it's constant. So it means that we have 5 different constant Y, but X and Z, they are changing because they have different grid. So this is the discrete function that I defined. And if we look at the results for this model, first factor of safety is 1.52. And if we look at all the slip surfaces on the model, these are all the slip surfaces that are generated. And if we back to the 2D one, you can see that this is the 2D critical slip surface for the model. And we ran the 2D model as well. And they match perfectly fine. We also have the option to look at the safety map. This is the critical region, and as we go further, the geometry and the model becomes less critical. So this is something that you can do for more complicated geometry, because slide 3 and slide 2, they share the same sort of search algorithm. So if you can find something, a critical steep surface in a slide 3, you can find the same critical steep surface in a slide 2 as well. So if we continue here, so this is the field that I defined in 2D. I took it as discrete function in 3D, and then we looked at the critical slip surface that was generated in the 3D model. The presentation is done. I think we responded to all the questions in the questions section right away. The video of this webinar will be available on our website very soon, and thank you again for listening to us.